We're now going to look at a more general longitudinal model with the intent of learning what happens when we add the influence of drag or a vertical offset of the lifting surfaces relative to the center of gravity. So we're just going to draw our center of gravity here, and weight acts down from there. And then for the vertical offsets here, we're actually going to start with thrust. And let's say that thrust is in this direction. And I'm going to align what's called the fuselage reference line with my thrust vector. So I'm going to draw a line through the center of gravity that's parallel to the thrust for this particular model. The fuselage reference line is a bit arbitrary. We're going to use that to measure angle of attack, but we're going to choose to measure or align it with the thrust vector, and then we'll give the distance of that thrust relative to that fuselage reference line. We'll call that h sub t, the height of the thrust. Okay, and then that fuselage reference line relative to the horizontal, we actually have three different angles that we're concerned about here. We're going to have a free stream velocity v infinity, and the angle between the fuselage reference line and v infinity is our angle of attack. The angle between v infinity and the horizontal is our climb angle, gamma, and then the summation of the two is theta. So theta equals alpha plus gamma. We are familiar with alpha and gamma from previous discussions, but theta is what's called the elevation angle. And the elevation angle basically is the angle that our nose is pointed up relative to the horizontal. And then, of course, the angle between the nose of our aircraft, or the direction that that's pointed, relative to the free stream is our angle of attack. And then if we're climbing, then the free stream is at an angle of attack, or an angle relative to the ground, and that's our climb angle. Okay, so then let's look at just a generic wing, and we're going to give it an offset here. I'm going to draw that a little bit exaggerated, but so that we've got a aerodynamic center there, and that is offset by, we're going to call that the h of wing, the height of the wing, and the distance back from the center of gravity, we're going to call that L sub w. And then that wing can be mounted, so this line here is parallel to the fuselage reference line, but that wing has a local mounting angle here that we're going to call alpha naught wing. And then the lift and drag in general are perpendicular to v infinity, but the local velocity that wing is seeing can be affected by downwash. And so we're just in general, we could account for downwash on any wing. And so let's see, if we were to measure the lift relative to an angle, so that's the lift of the wing, relative to a line that is perpendicular to the fuselage reference line, that would be offset by alpha minus the downwash. So I'm going to just put that in there. So usually we're just used to saying alpha here, but if we include the downwash, then it'll be alpha minus epsilon sub w, the downwash that wing is seeing. And then that's the same with the drag being rotated here relative to this line that is parallel with the fuselage reference line, and this is that same angle there, alpha minus epsilon w. So that's the drag on the wing. And then last of all, we can add the pitching moment on the wing. Okay, so those are our forces and moments that are coming from this wing, and they're offset from the center of gravity. And of course, we could add another wing back here. We'd have L sub h, the horizontal, and I'm not going to work through this, because the math is identical. So the free body diagram is the same for the horizontal. And actually you can add as many lifting surfaces as you wanted. If you wanted to have 3 lifting surfaces, longitudinal lifting surfaces, you could add them the same way. So so this is just the general influence of a wing. And for trim, now we need the sum of the forces in the x direction, the sum of the forces in the z direction, and the pitching moment about the y-axis, all to sum to 0. And rather than walk through that, it's a little bit tedious. I've copied some equations or typed out some equations here. So this is our axial and normal and pitching moment if we have a main wing and a horizontal stabilizer. So this is the force in the axial direction, the normal direction, and then the pitching moment. And then we're accounting for drag on the wing now that's rotated, by this alpha minus epsilon wing we've talked about here. We are, we're accounting for both the horizontal and the main wing in here. And then remember that, we're aligning this axis, our fuselage reference line, which is the direction of the axial force, that is aligned with the thrust. And I call this the coefficient of thrust. That's just C sub t is defined as thrust over 1/2 rho v infinity squared SW. And then we've got, let's see, in the normal direction, these are all of our forces there. And then the pitching moment gets a little bit crazy because we're including now not only offsets, so the distance aft of the center of gravity, but also the height above the center of gravity. And so we have the pitching moment from the wing, which is just its pitching moment from the aerodynamic center that just moves from that point to the center of gravity. But then we have offsets, vertical and horizontal offsets for the lift and drag on the wing rotated by that angle. Same thing with the lift and drag on the horizontal rotated by these angles here. So you can work through this. I mean, it's all just straight up statics. We're just summing forces and moments about the center of gravity, and we're accounting for the forces and moments from the thrust, as well as the main wing and the horizontal stabilizer. And you can see that the pitching moment includes the pitching moment from the thrust. There's a vertical offset of the thrust there. Okay, so in general, maybe one more thing that I should add here is that the lift on the wing, we can write the same way we did before. We can assume that that's linear with angle of attack, and we can include the mounting angle minus the 0 lift angle, and then we'd have minus epsilon of the wing, which is some downwash. So that would be the lift on the main wing now. And then the lift on the horizontal is the same as what we've said before. So in general, we've seen most of this before. We're just including a few more terms, including the vertical offsets here. So this system of equations here is highly nonlinear. And so we can't, we're not going to be able to just rearrange this and solve for alpha and delta E, right? So in the previous, with our simplified model, we could solve for alpha and delta E directly by simply rearranging these equations. But you can see that alpha is embedded in these sines and cosines everywhere. And so this is a very nonlinear model. One other thing that we need to point out is the drag on the wing, for example. The drag on the wing is related to the lift on the wing, so we would say it's some CD naught for the wing plus CD1 from the wing times CL plus CL and that's the lift on the wing, squared over pi times the Oswald efficiency factor, epsilon wing times the aspect ratio of the wing. Okay, so this is our general drag equation, and inside of drag, and we would have the same thing for drag on the horizontal, right? A very similar equation where we've got some CD naught, CD1, and then an Oswald efficiency and aspect ratio of the horizontal. So that would feed into the drag on the horizontal. So what I want to point out here is that alpha is actually also embedded inside of these drag terms, which, we're calling it CDW and CDH here, but alpha is actually embedded in there because it depends on the lift coefficient of the wing, and the lift coefficient of the wing depends on an alpha here, and we even have a CL wing squared in the drag term. We'll have the same thing in the horizontal drag, or the drag on the horizontal, and so anyway, this is very nonlinear, and so in general, in order to trim this aircraft, we have to use an iterative method or a nonlinear solver. Okay, so these are nonlinear equations, which means that we need to use an iterative method to solve for alpha and delta E, which is usually what, and also possibly our throttle setting tau, in order to trim this aircraft. Okay. So that's trim. Now let's talk about stability. And so you can take the derivative of this equation here, the pitching moment, with respect to alpha. And rather than work through that, again, I've typed it out what the solution would be. And so here's the pitch stability derivative. Again, a bit involved. And again, we're going to see that this is nonlinear. So where the previous model, our linear model, showed that the pitch stability derivative was a constant, or that the pitch is a linear function of angle of attack, we see that actually the pitch for this more general model is a nonlinear function of angle of attack. So we have, again, these alphas inside of these sines and cosines. And then we've also got like the lift coefficient here on the horizontal or on the wing that has an alpha embedded in it. And so you've got a alpha times an alpha here. Anyway, this is a very nonlinear equation as a function of alpha, I guess I should say. So so this is just our more general solution, and there's a few things that we can learn from this more general solution. So Phillips has 3 examples in his book, and I'm just going to talk briefly about what we learned from each of those examples. So his first example is 4.7.1, where he looks at the solution to these general equations, where so I guess I should point out 2 things really quickly. This general model includes not only these vertical offsets, but we've also, so we're including this these H sub W, or H sub H and H sub W terms, right? These vertical offsets, and also the vertical offset to the thrust. But we've also retained the nonlinearity due to these trigonometric relations. So we haven't applied the small angle approximations. And you could simplify these a little bit, if we did go through and apply the small angle approximations, but they would still be nonlinear, because you'd still have, for example, sine of alpha. The small angle approximation of that would just drop the sign. We'd have alpha minus epsilon wing here, but then you still have the lift coefficient of the wing that has an alpha in it. So we'd still have nonlinear terms in here, even if we use the small angle approximation, okay? So this first example that Phillips walks through is he sets all of the vertical offsets, so HT, H wing, and H horizontal equal to 0, and solves it, which still is a nonlinear system of equations as a function of alpha, because we retain those the nonlinear trigonometric components there. And we see that this gives solutions almost identical. It's like a 1% difference relative to the linear model. Okay, so almost identical to linear model, which is the simplified model that we discussed previously. So so there's not a lot of benefit in using this model if your vertical offsets are all 0 or very close to 0. That linear model actually gives very good solutions. Okay, so that's kind of the takeaway there from 4.71. And then 4.7.2, what he does is just say that ht is not equal to 0. So he moves the thrust vector up. He leaves the center of gravity and the main wing and the horizontal all aligned there on the fuselage reference line, but then just moves our thrust up. And shows that if we do that, that alpha really doesn't change. So the angle of attack between the linear model and our new model is about the same. So alpha is about the same. So our trim angle of attack doesn't really change, but delta E and the lift on the horizontal are significantly different. And that makes a lot of sense because we can come back up here and visualize what's happening. So basically he's saying that the main wing and the horizontal all lie on the fuselage reference line with the center of gravity, and we just have the thrust offset. Well, what that means, in order to trim the aircraft, because the thrust has to be equal to the drag, we're going that thrust has a vertical offset, and so creates a nose down pitching moment. And so at least if the thrust is offset in the positive direction there. And so in order to trim the aircraft with our horizontal, we're going to need to create a nose up pitching moment, because this would be creating a nose down pitching moment. And so we're going to need to have a larger lift on the tail, actually negative lift. And so we'll be pushing down back here, which requires a different elevator deflection back here, in order to trim out that the pitching moment due to the thrust offset. Okay, but the trim angle of attack really doesn't change significantly for that case, relative to the case if the thrust were not offset vertically. So okay, so that's kind of the takeaway from that example. And then 4.73, what he does there is that he takes the wing instead and offsets it vertically. And he looks at this example where he's got a canard, so he's got a little wing here and a center of gravity here, and then what he calls a high wing canard configuration. Okay, so the main wing is offset from the center of gravity, but the canard is not. And then he looks at lift, drag, and pitching moment as a function of angle of attack. Okay, so on this axis we have alpha, and then he plots lift, drag, and pitching moment. And so let's just kind of sketch out what happens here. So of course drag is going to look something like this. This is CD as a function of angle of attack. Our lift is linear with angle of attack, so that would be CL. At least, below stall, it's roughly linear. And then usually what we're used to happening is that at some trim point, so let's say we're trimmed at this angle of attack, we have this drag coefficient and this lift coefficient. From the linear model, we're used to thinking of our pitching moment looking something like this, where we have some pitch slope, some pitch stability derivative that must be negative in order for this to be trimmed. And so we're used to our pitching moment looking something like this, but in this case, we get a pitching moment that looks something like this, okay? So this is the true pitching moment, including the non-linearities, and if we didn't have a vertical offset, then we'd get a pitching moment more like what I've drawn in blue here. And so this opens up a really good discussion on pitch stability. Now, technically speaking, this aircraft is still stable in pitch around that trim point. So if this is where we're trimmed, our first derivative with pitching moment with respect to alpha is negative, and so our we're still stable because we've got a negative cm alpha there. But and actually we're stable if we move back here, we're stable. This is the point where we would get the largest restoring pitching moment. So if we were trimmed at this point, but because of turbulence or something, we got bumped to a different angle of attack, a lower angle of attack, then this would still create a very large restoring moment, because we'd have a positive pitching moment and a lower angle of attack than we need, and so it would bring our nose back up. And actually, let's also walk over here and look over here. If we get if because of turbulence we had some really large angle of attack, we see that we get very strong negative pitching moments, and so that will also return us back to this point. The problem is when we go actually past this point here. So you might be thinking, no, this is the point where we're going to have problems. Actually not. If we get an angle of attack that bumps us clear down into this region, then we still have a restoring moment. We still have the correct sign on that restoring moment. It's going to bring us back to this point. But if we get an angle of attack that bumps us past this point here, now we have a negative pitching moment. It's less than 0, and we're at a really low angle of attack, and that will actually drive us to lower angles of attack, to more negative angles of attack. So this is similar to the condition that we talked about earlier about a ball in a bowl, where it can be, this is kind of this condition here where we're stable as long as we don't move too far away. But if the ball gets bumped too far to one side, then it can deviate away from that trim position and become unstable and move away from trim. So this is what happens when we have a large vertical distance between our main wing and our center of gravity. And actually this is a very common thing to be aware of for hang gliders, because they have a very high wing, and then the human obviously is a lot of the weight of that aircraft, and the human sits significantly below that main wing, and so you have a significant difference in the height there. You know, have a vertical offset of that wing from the center of gravity. So anyway, so that's kind of the takeaway here for that example. And then one last thing that is worth pointing out is the importance of this type of analysis on amphibious aircraft. So let's come back up to our free body diagram here. Amphibious aircraft usually have the thrust offset vertically from the center of gravity significantly. And the reason for that is that they need to get the propeller out of the water. So let's just look at some examples here. You can just do a search for amphibian aircraft and come up with a lot of images here. This is kind of a well-known newer aircraft called the Icon A5. And so you can see that propeller sits up a ways, because this is meant to land in the water. So your propeller has to be up a way to keep it out of the water. And so that propeller often is sitting a ways above the center of gravity. And as you flip through these different pictures here, you can see that that's kind of the trend. So let's talk about what that means. During takeoff, this is especially important, because we've got thrust here that's vertically offset from our center of gravity, and we're at somewhere near full power, so we got a lot of thrust. That means we have a very large nose down pitching moment here due to the thrust. And so that means from our elevator back here, even if the elevator is aligned with the center of gravity, we're creating a very large nose up pitching moment from the elevator in order to offset the nose down pitching moment from that thrust. And so that's fine unless we have an engine failure on takeoff. Now, if that happens, then we suddenly lose our thrust vector, and instead of thrust, we actually get drag up here, because we have a stalled prop that's creating drag. And so this now creates a large nose up pitching moment, and we're creating a large nose up pitching moment from our elevator back here. And so if the pilot doesn't correct quickly, the aircraft will just stall because it will quickly pitch the nose up and can stall the main wing of the aircraft. And so this can be a really dangerous scenario. And another dangerous scenario is actually on landing when we come in, if for some reason the pilot has to do a go around, because on landing we have very little thrust up here, and maybe we're even we have our thrust at idle, or even to a point where there's drag up here. So we've got a nose up pitching moment, or well, we're trimmed as we come into land, and our horizontal is offsetting that in order to trim the aircraft. And then if we have to do a go around, then suddenly we have to go to full throttle, or ramp up the throttle quickly, which is going to push our nose down. It's going to create a nose down pitching moment. And so at the same time as we're increasing throttle, we've got to be pulling our nose up with the horizontal back here in order to keep that aircraft from just doing a nosedive into the ground. And so, and again, if the engine has any issues, you just have to be able to respond quickly with your horizontal or with your elevator in order to keep the aircraft trimmed. So anyway, these are just some things to be thinking about as you're designing aircraft, and the types of aircraft, the types of missions that you look at are obviously affected by these types of these diagrams that show where the forces of moments are on the aircraft and how we're going to face some of these scenarios. So this is a more general longitudinal model, and the quick takeaway is that this produces very nonlinear equations. These can be solved using iterative methods to get our trim conditions, alpha, delta, E, and our throttle. Our stability now is no longer a line, but can be a curve, and that depends, of course, on how large the vertical offsets are and things like that. But in general, this model can capture more of the physics of what's going on than our simplified model can. And it's not really that complex. I mean, we're talking about sines and cosines in here, and sure, you have to solve this iteratively, but it's not really terribly difficult to solve. We just have to solve it numerically.